In the computer world, if I ask, what is the one thing which you use every second? The answer would be very predictable. Operating system. The one you are staring at right now. But if we ask anyone what it actually does, they'll say it runs apps. That's like saying a car engine makes the wheels spin. So, what our goal is, by the end of this series, we won't just learn the theoretical aspect. Yes, we will be learning the theory that actually gives us the bigger picture. But apart from that, we'll try to build one from the scratch. We'll also see the code base of actual OS. So let's boot up. Before we even start talking about OS, let's talk how this whole series will work. See, we will not be just reading the slides at each video. For every single topic, we'll go through like 3 phase cycle. The very first one is like theoretical aspect. So we'll learn the theory, all those textbook definitions, algorithms, and classic problems, so that we could get the bigger picture. So the phase one will be theoretical aspects. Then for the phase two, what we'll do is we'll try to open up the real OS source code and we'll find exactly how that particular theory whichever we read is implemented. And just the real C and assembly language out there. We'll read it, we'll understand it. So the second phase will be the internals of it. And for the final phase, that is phase 3, we'll try to build it ourselves. All those bootloaders, kernel, processes, file system, write it from scratch so the knowledge becomes the muscle memory. So phase 3 will be hands-on build. So we'll start with very fundamental question, that is what even is an OS? And we'll see in the textbook that different definitions are like it is a resource manager, an extended machine. And that's true in a sense. And the simplest definition which we could understand or which which exists there is an OS is a program which acts like an interface between computer hardware and the user, the end user, like us. Actually, hardware is stupid. It's just copper, silicon, and some electricity. So it does not know what a file is. It doesn't understand what a window is. And it's the OS kernel that takes the raw metal and wraps it in the abstraction. Whether it's files, processes, sockets, memory spaces. That's what extended machine is. We program against a nice interface, not just the bare metal. And other aspect of kernel is also like it also acts like a bouncer. It manages all the resources. That is the reason no app can touch the disk or screen directly. That's why you'll see that a web browser cannot crash your entire computer because the kernel isolates it. See, we'll see all those kernel and all those jargons once we'll go in depth of everything. For the time being, if you want to understand simple point, so you could depict as a OSS interface between user and computer hardware. The second thing is it also manages resources. and it is a basis for application in system program. We will see what is application and what is system program. Because those things are also managed via OS itself. So this is high level diagram of it, where at the very beneath we have computer hardware, which is abstracted via operating system. Actually there is kernel in between, we'll see it later. And then we have specialized programs known as application program and system calls and all, which we'll see. But then we have our end users, like which we have depicted here with u1, u2, u3. You'll find this diagram wherever, like all the places you could see. So that's the standard diagram which everyone follows. But now let's come to like application programs and system programs. What are they? Let's come to that. So second thing is application programs versus system programs. So if you want to understand application programs, so these are the programs designed to do some specific task, and these are used by the end users. So these are the programs what we install, like Chrome, Spotify, VS Code, and all those things. They exist to serve the user directly. They talk to the OS, not the hardware. So we could write specialized programs to do a specific task. And who uses it? Or what it serves? It serves the end user directly. And they would talk to the OS, not the hardware. Whereas in case of system program, so these are the programs that actually sits between the apps and the kernel. Imagine your terminal, that's a system program. The cell, the compiler, the linker, even the file explorer, all system softwares. They help manage computer itself. So the kernel is at the very core, but you rarely speak to it directly. We use system programs as a translators. So what it does is it talks to the kernel, and then kernel talks to the hardware. So if we want to summarize it, we could say that it manages the like core system or the computer itself, like memory, CPU, etc. And also like they actually runs in the background continuously, and it won't be requiring the end user interaction. Third one, we could say that it talks to the kernel. The next thing we'll be seeing is functions and goals of an OS. So let's start with functions of OS. See, on a on a like a summary level, we could say that it will act as an interface, it allocates memory, and then security and all. But like the main six functionality of it is, the very first one is process management. It will start, it will pause and kills all the programs. Then memory management, it gives RAM to all the apps and then it will take it back. The file system, it actually turns the raw disk blocks into files and folders. Other function would be IO management. It talks to keyboard, mouse, GPU. And then comes the security. See, we have so many processes. So it keeps each processes from, like it stops each processes from eating each other. And then comes the networking. It manages the Wi-Fi card so that we all could watch our favorite videos. So if we want to summarize, we could summarize in the very first one would be process management. The second would be memory management. See, we'll see all those things in depth. It's just an introduction video, so that we could have a bigger picture, we'll understand functions and goals of the OS. And the third one, what did we discuss? I guess file system or IO, whichever like file system we will write. And the fourth one is input output management. Fifth one could be security. And the last one is networking. So these could be six like important functions of OS. Now, if we talk about goals of an OS, so let's first build it, draw it. If we talk about goals of an OS, so the whole thing I could summarize is like the whole thing exists for two main reasons. The very first one is convenience. The OS is the one which makes the computer usable. Imagine having to manually like set disk head positions every time you save a file. So won't it be like disaster for us? Second one is efficiency. The OS will always try to make sure that expensive CPU and RAM aren't sitting idle while we are thinking. So it will always try to optimize the uses of CPU and RAM. So the two goals which we could depict is, the very first one is convenience. Like forgive me for the spelling. I guess this is the spelling. And the second one we discussed efficiency. So convenience in terms of user experience and efficiency in terms of how like it handles CPU and RAM, all the resources it is having. So it's like maximizing the efficiency or use of resources. Now there's a one question which I'll leave you with. You need to research it. You need to find your own answer. So let's suppose if an OS is all about efficiency, so why does like gaming PC sometimes lag even when the CPU is at 100%? What's the actual bottleneck? So try to find out. If you're a gamer, you would already know it. I assume that maybe you will not. So try to find out that answer. If you want, I would repeat. Let's suppose if an OS is all about of efficiency, so why does my gaming PC sometimes lag even when the CPU is at 100%? So what's the actual bottleneck? So the last thing for this video which we'll be studying is types of operating system. See, operating system didn't start with something like very flashy or like very uh, sophisticated system. They actually evolved out of pure necessity. And like if you want to understand in very simple and short way, so let's try to understand it with the help of different types of operating system. So the very first one, let's say batch OS. So think of it like a simple stack of punch cards. Imagine like you're writing a letter, putting it into the mailbox and waiting days for a reply. Similarly, in early computing days, like you used to give the computer a pile of cards or what we say as batch, and we just walk away. And then we came back later for, let's say, printout. And there was actually no live interaction, or we could say zero live interaction. Then there comes the second kind of OS, which is multi-programming. So if you want to think like multiple jobs are like loaded into the memory at once. It's like a chef cooking three meals at the same time. And when the one thing is happening, chef is doing the other stuff. So in this stage, if a program is actually paused to wait for a printer, the CPU instantly switches to a different program. So what happened is, we now know that we'll need to switch to different program if CPU, like if the very first program is waiting for some IO or something. So we are doing multiple programs at a time. Now the third one is time sharing based or time sharing OS. So it's interactive terminals for multiple users. So imagine a chess grandmaster playing 50 people at once. And he is actually moving rapidly from one table to another. So the computer actually switched between users so fast that every single person felt like they are having the entire machine to themselves. And this was the time when the users actually felt the true live interaction, because everyone is feeling like, oh, I am having the entire machine. Now comes the real time OS. So think of system for rockets, drones, or something like that. So the OS isn't about average speed. This particular OS isn't about average speeds. It is about absolute certainty. If a drone needs to adjust its rotors to a wind in like 2 milliseconds, then even like minute fraction of delay could actually mean a crash. So in this real time OS, it prioritizes strictness, unbreakable deadlines over everything else. So that is real time OS you'd find in rockets, drones, and etc. Now comes the distributed OS. It's like a cloud of connected nodes. If you want to think of some analogy, think of ant colony, like hundred of separate ants works together so perfectly that to a different like to us it feels like they are one single organism. Similarly, in OS also, the OS connects dozen of individual computers and make them look like one massive supercomputer to the user. See, you would find a bunch of example for this also. You could actually research. I'm just trying to give you analogy. Then we came to mobile OS, and we all use it, whether it's iOS, Android. So this is the modern smartphone software that we actually use every day. Whether it's responding instantly to finger touches, saving as much as battery life as humanly as possible. So that's it for this video, and we'll see you on the next video. Till then, keep studying, keep learning. Thank you for now. Bye bye.